Yeah, thank you so much. Popper and Lakatos were a big inspiration and a big source of ideas when I was working on my PhD thesis, which was concerned in the normative foundations of various standard practices in statistics and machine learning. So I was really excited to present this stuff here, and also like weirdly nervous because this is Lakatos' institution. Somehow it feels more more pressure.
Got this, Casey?
Yeah. So I like this Popper's picture in the philosophy of science. I think we're all familiar with this kind of cartoon. Science progresses through a series of highly testable conjectures, followed by dogged attempts at refutation. Now, Popper's view, simplicity reflects testability. So Occam's razor is actually directing the scientist's attention to the simplest and therefore the most highly testable theories, and that's how the game goes. Now I like this picture. It has something like heroic and existentialist about it. You know, the heroic scientist forgoes the comforts of confirmation theory. You know, faces the true horror of the problem of induction squarely in the face, and you know, subjects her favorite theories to withering criticism. You know, that's really cool, I think. But why I think this is anything more than a series of bold mistakes yielding to new and bolder mistakes, right? Is science just like Sisyphus, you know, rolling the boulder up the hill and then having it just like roll back down? And we just have to imagine the Popperian happy, and that's all there is to it, you know? Or is this whole process going somewhere? And now this is also Lakatos' objection. He says Popper offers a methodology without an epistemology or a learning theory, and confesses explicitly that his methodology may lead us epistemologically astray, and implicitly that ad hoc stratagems might lead us to truth. Popper was aware of this problem, and he hoped to show that the critical method leads to theories of increasing truth-likeness. And you know, that is according to Lakatos what needs to be shown, and only such a demonstration, or he calls it here an inductive principle for some reason, can turn science from a mere game into an epistemologically rational exercise, from a set of lighthearted skeptical gambits pursued for intellectual fun into a more serious fallibilist venture of approximating the truth about the universe. But, I mean, unfortunately, Popper's notion of truth-likeness was famously trivialized by Pavel Tichy and David Miller independently, shortly after being proposed. And the problem with it was a technical problem. For any two false theories, it turns out that neither is more truth-like than the other, which is a shame. But, Odie and Ninilaudo made more and more sophisticated iterations of truth-likeness, definitions of truth-likeness. And these did surmount the earlier logical problems with Popper's definition. But the problem of estimating, so even though they had solved the metaphysical problems in a sense, the problem of estimating verisimilitude is neither more nor less difficult than the traditional problem of induction, according to Ninilaudo in his book. So to estimate which of two competing theories is more truth-like, you have to introduce something like a subjective prior, and then it generates another problem of somehow demonstrating that inferring the apparently more truth-like theory is conducive, in fact, to increasing truth-likeness. So it's a shame, because we were trying to make progress on the problem of induction, and instead we reduced it to a problem equally difficult, I guess. And, Lakatos was onto this too. He said, from the statement that the verisimilitude of our scientific theories can increase, it only follows that our knowledge can grow, but without our knowing it. If so, even Popper's newly found fallibilism is nothing more than skepticism together with a eulogy of the game of science. Popper's theory remains a metaphysical logical theory which has nothing to do with epistemology. So, I think Lakatos is saying, well, without some way of knowing which of two theories is actually more truth-like. We haven't actually gotten anywhere. And, you know, it's not like he was any better off in that regard. So in order to get amped for this conference, I read Larver's book. And Larver puts this, I don't think this is coming out of the mouth of Larver exactly. I think Larver's putting this objection in the mouth of the realist. You know, so he says, as realists, we agree with Lakatos and Popper that the aim of science is truth. And as rationalists, we expect means to be properly connected with ends. Specifically, we expect scientific methodology to be connected with the aim of science, that is the truth. In Lakatos, there is no logical or causal connection between his proposed methodology and the agreed aim of increased verisimilitude. All he offers is his metaphysical inductive principle, supported not by argument, but by pious hope. You know? So yeah, bummer. So where do you go? And the move that I want to make is something like the move that virtue ethicists make. So here's Zagzebski in her book. She says, since justifiedness is a property of a belief, it's very difficult to adjudicate disputes if the belief is treated as the bottom level object of evaluation. Instead, we focus on the deeper concept of an intellectual virtue and treat the justifiability of belief as derivative. So the idea is something like, instead of focusing on these low-level objects of belief, we like move up the type to something like virtues or characters, and we try to justify various kinds of good character, and then treat the beliefs generated by those characters as derivative. I want to make something like the same move, except I don't want the bottom level object of evaluation to be theories. I want it to be methods, or like dispositions to generate theory on the basis of evidence. So we're doing the same kind of move to a higher type kind of thing, a character or a method. And that was the point anyway. We wanted to justify scientific method or the critical method or something like that. Not to say that any particular episode in science necessarily was progressive. Okay, so first pass. Say that a method for answering a scientific question is progressive if and only if the chance that it outputs the true answer is strictly increasing with sample size. Okay, so for chance, insert your favorite notion of chance, objective chance. I like objective chance, something like propensity. Just put in the Popperian one, why not? And notice that this notion makes sense, even if it doesn't make sense to ask which of two false theories is closer to the truth. I mean, if you accept that some answer to a scientific question, or one of the answers to a scientific question is the true one, you want the method to have the chance that it gets the right one to be increasing with sample size, and that has nothing to do with comparing the truth-likeness of any two answers. You don't need a theory of which of two false things is more truth-like in order for this thing to make sense. But okay, you might say, I don't believe answers to scientific questions are literally true, and here we can actually use the truth-likeness theory. You could say, okay, a method for answering a scientific question is progressive if and only if the chance that it outputs the most truth-like answer is strictly increasing the sample size of the answers currently on the table to the question that we're working on. Or the most useful, if you want to go that way. It doesn't really, this kind of parametric thing here. Okay, strict progressiveness, it turns out, is not feasible to achieve in standard statistical situations. So we need to back off for a little bit, but treat progressiveness, strict progressiveness, as the regulative ideal. So let's say a method for answering a scientific question is alpha progressive if the chance that it outputs the true answer converges to 1 as samples increase and never drops by more than alpha. So this is just just means to be a suggestive picture where we're plotting the chance that the method outputs the true answer against the sample size, and we notice like this is not a very progressive looking method because as sample sizes increase, the chance that you output the right answer is dropping precipitously. It's like the method has a tendency to fail to replicate correct things as sample sizes increase. And this one, we keep the backsliding to a minimum. The backsliding is kept rather small. Now, surprisingly, you might think that progressiveness is just like a standard feature of standard statistical method. Like, it just means that collecting larger samples is a good idea, generally speaking. But surprisingly, many standard statistical methods aren't even approximately progressive. So for example, Chernick and Liu in this paper, the sawtooth behavior of power versus sample size and software solutions, they're plotting the probability that a certain hypothesis test rejects correctly against sample size at a particular parameter. And they notice that you have these large oscillations in power. Power is the probability of correctly rejecting the null at a particular parameter. And you get this sawtooth shape, which is worrisome because it means that, like, at sample size 43, your tendency to correctly reject is significantly worse than at sample size 40, which sounds scary. Yeah, the method has a built-in tendency to fail to replicate true results at larger samples. Weird, right? What would this actually mean? Like, suppose you were doing a replicating study with a larger sample of some new drug or something for treating migraine, and you did your first study at sample size 100. You notice an effect, and then you propose to the funding agency, let me replicate at a larger sample size and collect more, get more people into the study. But I've done my power analysis, and we actually have a lower chance of replicating successfully. I think the agency would be like, no, that's epistemically perverse. That's perverse in a variety of ways. Why would you expose more people to side effects or something like that for a lower chance of replicating correctly? That's just not right. Okay. So here's a theorem for my dissertation. So if you can, I don't expect you to understand all the terms here. I owe you definitions, but this is just like foreshadowing. If you can enumerate the answers to a scientific question in agreement with simplicity, in agreement with the simplicity order, then there exists a progressive solution to that question. What do I mean by progressive solution? I mean, it's alpha progressively solvable for every alpha greater than 0, which means that you can get the degree of backsliding down arbitrarily small, although you can't eliminate it. And in turn, every alpha progressive solution satisfies a kind of Occam's alpha razor. So Occam's razor is a necessary condition of, like, virtuous convergence without a lot of backsliding to the truth. And I think this is neat because it's not circular. It's a not circular, and for my taste at least, it's an epistemic and not merely pragmatic justification of Occam's razor in statistics. So building in a tendency to violate Occam's razor into your method amounts to building in a tendency to fail to replicate true results. And the cool thing is, a carefully calibrated Popperian methodology can ensure that the degree of backsliding is arbitrarily low. So the methods, the progressive solutions, well, one of the ways of building a progressive solution, it proceeds a lot like a conjecture and refutation type, simplicity-guided conjecture and refutation type strategy, but carefully calibrated so that all the alphas work out. Okay, I think I just want to jump up and down about something here. So I want to jump up and down about, traditionally we've conceived of epistemic justification as opposed to merely pragmatic justification in this synchronic way. So if you read the SCP on simplicity, Alan Baker helpfully, I love it when people say exactly what you want them to say, so you can disagree with them directly. So it's just so wonderful. They're the best friends. Justifying an epistemic principle requires answering an epistemic question. Why are simpler theories more likely to be true? Well, I don't pretend to have any reason to think that simpler theories are more likely to be true. What I'm claiming is that a systematic preference for simpler theories is a necessary condition for a certain kind of convergence to the truth. A virtuous looking one. Yeah, a nice one that doesn't backslide too much. That's not the same, but I think it's still an epistemic justification. I just think, if you demand synchronic justification, you get into this despairing kind of attitude. So for example, Larry Loudon in this paper in 2004 says, no one has shown that any of these rules is more likely to pick out true theories than false ones. It follows that none of these rules is epistemic in character. He has in mind, for example, simplicity, Occam's razor. That's one of the things he's talking about. But again, you don't need to, I think the standards here are too synchronic, too high. You don't need to show that the rule is more likely to pick out true theories than false ones. And going diachronic allows us to demonstrate that a systematic preference for simple theories is a necessary condition for a diachronic notion of progress. I think that's still epistemic. It's still epistemic for my taste. I don't know. And why not? Okay, so how am I doing?
You've done 15 minutes. You got 15 more.
Yeah, okay. So just to flesh out the concepts here. So the problem context, we have a set of models or a set of contextually relevant epistemic possibilities. Each model determines a probability distribution over the data that you're going to observe. A question, for the purposes of this talk, partitions the set W into just a countable set of answers. And for every model, M, Q, like fancy Q sub M, is just the answer true in that model makes true. It's just the cell of the partition that the model is in. What's a method? A method is it's a function for every sample size, from samples to conjectures. And a collection of such functions is a solution to the question if no matter which model is actually generating the data, the probability in that model that the method outputs the right answer in that model converges to 1 as samples increase. So it has a solution if you can converge to the right answer. No matter which models do. No matter which answer is right, you can converge to the right one. And a question is solvable if it has a solution. A solution to a question is progressive if for any two sample sizes and for any model, the probability in the model that the method outputs the true answer in that model is strictly increasing with sample sizes. Okay, we have to back off, like I said. A solution is alpha progressive if it's almost monotonic. If for any two sample sizes, the probability of getting the right answer at the larger sample size plus alpha is bigger than it was at the smaller sample size. And we say that a problem is progressively solvable if it has one of these alpha progressive solutions for every alpha, which means although I cannot eliminate backsliding entirely, I can, make it arbitrarily small. Okay, I need to tell you, because this is like supposed to be about Popper, what it means for a hypothesis to be statistically refutable. I don't want to belabor this point. I have a paper about it recently. But roughly we say that a hypothesis is alpha refutable if there is a consistent hypothesis test of that hypothesis with a significance level alpha at every sample size, which means that if it's false in every alternative, the probability that you reject it converges to 1. If it's true, the probability that you incorrectly reject it is bounded by alpha at every sample size. And we say that a hypothesis is refutable if it's alpha refutable for every. We get the bound on falsely rejecting. We can take the bound on falsely rejecting down arbitrarily small. This is just writing that same thing in symbols. So if the hypothesis is false, the probability that you reject it converges to 1 as sample size increase. If it's true, then the probability of rejecting it incorrectly is bounded at every sample size by alpha. And actually, you can come up with fancier versions of refutability. You might keep everything we just said, but also it's not only that the probability of falsely rejecting is bounded at every sample size, you also want it to go to 0 as sample sizes increase, and you might also want this other nice monotonicity property, that the probability of rejecting correctly is also increasing almost monotonically. And we say a hypothesis is monotonically falsifiable if it's alpha monotonically falsifiable for every alpha. And so in this paper, I have a proof that like under some mild assumptions, the statistically refutable hypotheses, like the weak notion, are exactly the monotonically statistically refutable ones. Whenever you can achieve the weak thing, you can achieve the strong thing. Of course, if you achieve the strong thing, you can achieve the weak thing. And the hypotheses are exactly the closed sets in a familiar topology on probability measures. And if that's meaningful to you, cool. If it's not, it doesn't matter. The point here is that insisting on monotonicity doesn't make any fewer hypotheses falsifiable. Okay, what's simplicity? This was Popper's idea, one of the ideas in the book. For any, wait, that's wrong. Well, for any two models, we say that A is as simple as B, if and only if all refutable consequences of B are refutable consequences of A. I think disjoint shouldn't be there. I think this is Popper's one of Popper's proposals in the book. I actually think this is, yeah, there it goes. The disjoint went away. This confounds logical strength and simplicity because, like, one of the most complex possible thing you can say on this definition is to suspend judgment between the answers. And suspending judgment, I don't know, it's not the same kind of thing as saying something which is too complex given what the data you've seen. So the first amendment I make to this is to say, we mean competing answers. Yeah, for two competing answers, A is as simple as B if all refutable consequences of B are refutable consequences of A. That's just the first amendment to Popper, so we don't confuse logical strength and empirical relations of underdetermination. But then you have some other fussy problems, like the tack-on problem. For example, guessing that the curve is linear is simpler than the curve is quadratic, but linear, either the curve is linear or the cat is on the mat, is now no longer simpler than quadratic. And it's kind of this awkward, annoying, typical freaking philosophy thing. So what do you do now? And you have to bite the bullet in some way. So the adjustment that I make here is, for any two disjoint sets of models, we say that A is as simple as B if all refutable consequences of B are consistent with A. They're not entailed by A, they're just consistent with A. In most model selection problems, the simplicity order generated by the problem, it will be the same. Because generally speaking, when people pose questions, they have a nice uniformity property that makes it so that the two simplicity orders are the same. Okay, so theorem. If the answers to the question can be enumerated in agreement with simplicity, now you know what simplicity means, because it was just about refutable consequences. And you know what I mean by refutability. I mean statistical refutability, so you know what I mean. I'm not just saying stuff. So if the answers to the question can be enumerated in agreement with simplicity, then it is progressively solvable. And if this is an enumeration of the answers, agreeing with simplicity, a progressive method can be constructed by attempting to falsify larger initial segments, like conjectures and refutations, but you have to manage the degrees of monotonicity of the constituent methods in such a way that the whole thing maintains the almost monotonic property. Okay, last definition almost. So what's Occam's razor? A solution satisfies Occam's alpha razor in every model if the chance of conjecturing an answer more complex than the true answer is less than alpha. So what is it saying? No matter which model is the correct one, your method has the property that in that model, the probability that the method conjectures something more complex than the truth in that model is bounded. So that's like uniform. No matter which answer is the true one, you never have a high chance of conjecturing something more complex than the true one. You always err on the side of simplicity with high probability, basically. And so we say that a solution satisfies Occam's alpha razor if whenever this, the answer true in M is simpler than some other answer, the probability in M that you conjecture theorem. Every alpha progressive solution satisfies Occam's alpha razor. So every progressive solution with high probability errs on the side of simplicity. Okay, that was the thing that I promised you guys. Okay, phew. What did I promise? A non-circular epistemic justification. Hopefully you don't find that this is non-circular, that this is circular, and hopefully you don't find that this is merely pragmatic. And a carefully calibrated Popperian methodology can ensure that the degree of backsliding is arbitrarily low. I haven't actually proven that to you. You have to take my word for it that when you construct progressive solutions, one way at least of constructing a progressive solution is by doing this carefully calibrated scheme of conjectures and refutations. And every way of constructing a progressive solution is going to have to err on the side of simplicity, and simplicity interpreted in a Popperian way, but not literally the way that he